We talk about oil. Oil comes from the decomposition of plants from about 300 million years ago. Most of it's deep in the surface, but there are some places, such as the La Brea tar pits in Ojai Valley, California, where oil comes right to the surface. Not a lot, but oil is found throughout the world. As you can see on this map here, the oil reserves, as I said, are found throughout the world, but nearly half of them are within a small area in the Middle East. Now, this is liquid oil right here, liquid petroleum. 5% is in North America, a fair amount in Central America, Eastern Europe, as well as the what was considered China and Asia, and small areas in Africa as well as Oceania. However, as you can see, a majority of it relies in the Middle East. Interestingly, in the last 20 years, they've found technology to extract oil from oil shale. Shale is real thin, easily pulverized rock with oil immersed through it, and they can actually remove the oil from the rock by crushing it and separating it. As you can see, there's a great amount within Canada and North America, and that's part of the reason our oil prices have gone down in the last 10-15 years. The process of getting gasoline and other fuels from crude oil is actually called cracking. It's a very simple process where you heat it up, not boiling, but you want to separate into different layers. And the heavymost layers are going to be your heavy oil, your lubrication oil. Vaseline comes from that. Higher up, kerosene. Lighter than that is gasoline. Naphthalene, which is even beyond that. Natural gas is at the very top. The coal reserves, which powers a significant amount of energy throughout the world also, are found mostly within Russia as well as the eastern United States along the Appalachian Mountains, as you see here, with a fair amount in Canada and Alaska. Hubbard's Peak predicted that as more and more oil would be used, and then it ran out, where you see the little gray curve here, you would have greater problems within the population of the world. Unfortunately, or fortunately, depending on how you look at it, as we discovered newer ways of getting oil out of the ground, which I'll talk about a little bit, as well as using oil shale, we've increased this desire for oil. And as you can see in the peak on the right, we still have more oil than we ever had before. A little comment on here, and I've been hearing this for 50 years myself. We always hear about how much fossil fuel we have left over, and these numbers have not changed since I was a child. 114 years of coal, 52 years left natural gas, 50 years of oil. The problem is these are estimates at best. And what I say by that is this is estimating what's in the ground. We have been never allowed to go into Iraq and see how much oil is really left. We have never allowed to go into Russia and say how much coal is really left. And part of that reason is, if you remember economics, if Iraq or Iran or Syria, somewhere in the Middle East, said we have 1,000 years of oil left, the price would go way down and they couldn't charge as much. So it's just economic convenience. Why would a country tell you how much they have? So these are just rough estimates. And like I said, they've not changed since I was a child. We hear about cleaner sources of fuel. Why aren't we using more of them? Since over 3/4 of is being used by oil, coal, or gas. 6% nuclear, hydroelectric, which is 2%, and the other one, solar, wind, and even tidal, 11%. Why aren't we using more of them? And I'm going to show you some of the problems with these new sources thus far. In the 19th century, scientists by the name of Michael Faraday actually discovered how to make electricity by basically spinning a magnet around a bar with copper wiring around it. And you can create one of these at home if you actually like. This wheel spinning creates electricity. The faster it spins, the larger the magnet, the more electricity it's created. So when you see a dam or a windmill or even a turbine, the way it makes electricity is by spinning quickly and spinning a magnet around. Hydroelectric power, in other words, making electricity from a dam, the water's under pressure because it's dammed up. And you can see the little tube going through it spins a turbine. That turbine is the circular magnet that spins very, very quickly. The generator has the iron around it, and that powers those transmission lines. This is an example of a wind farm in Indiana. It's about 300 feet tall. And again, how does it make electricity? It spins around a magnet around an iron core with wire going through it, generating electricity. People often ask, well, why don't we have more wind power? And there's two reasons for that. Number one, you can see where the windy areas are throughout the United States. Atlanta's not one of them. Along coasts, you'll see that, because where the ocean meets the land, you have a lot of wind. And in the Great Plains. However, the second problem is that when you have an aluminum or copper wire traveling hundreds of miles, it loses its power. For every 100 miles of aluminum wire on a high tension power line, these pylons, it loses 30% of its electricity. So after 300 miles, there's no electricity left. So as you can see here, we could set up along the coast, but let's say in Savannah, but by the time we got to Alabama, there'd be no power left. That is why we don't have more windmills generating electricity throughout the United States. It's not windy enough, and where it is windy, it can't reach far enough. Solar power. Solar cells have gotten about 30 times more efficient than they were 30 years ago, and technology is continuing to increase. However, this is a solar power facility in the Mojave Desert, and it's powering 140,000 homes, as you can see on top of the slide. If you look, to give scale here, if you look between these towers, you'll see trucks and cars to give you scale. You can see how large a facility this is. This is probably about 20 times the size of a coal plant or an oil plant or even a dam that generates electricity. There's a lot of sun needed, and when you have a lot of sun, with the inefficiency of the solar cells right now, you need a lot of land. So 140,000 homes, look how large this is, and you compare it to the city of Atlanta, how much land would you need? And then similar to wind power, there's not those ideal solar areas throughout the world. Obviously, closer to the equator you get, you have more sun. And the problem is, you can say this is the windmills as well as solar power. If you don't have enough sun, it's going to cost you more to put in the solar panels than the energy you're getting out of it. And that's cost inefficient. Geothermal flash steam power plants. Geothermal, this is from deep in the earth, from plate tectonics, which you'll study in a class next week. With the movement of the earth, same thing that creates earthquakes as well as volcanoes, will heat up water under the ground. And again, we can get the water out. It's superheated steam. It will spin a turbine as we had before. Interesting idea. And again, the same problems we have with solar power as well as wind power right now. We don't have geothermal areas throughout the world. In fact, we look at it as what we call earthquake zones, volcano zones, in the Pacific, going from Japan up through North and South America on the west coast, and then down through Australia. That's called the Ring of Fire. There's small volcanoes, earthquakes, and tidal waves created there than anywhere else in the world because of plate tectonics. Good for geothermal, but you can see throughout most of the world, there's not that many geothermal hotspots. Tidal energy. This is the movement of the tides. Anytime you have movement, you have energy. And the tides are created from the Earth's rotation around the sun as well as the moon's rotation around the Earth. You can see here this is an experimental station. You've got these propellers that move back and forth, again spinning, creating electricity under the tides. Very early on, could be a great protection technology in the future. Similar to tidal technology in the previous slide, wave technology. Waves move back and forth, and what does that cause? That causes movement back and forth. Very early technology, still experimenting with it, but we don't know where the future could lead with us. And ultimately, the position of where we have ideal tidal and wave energy locations is going to be along coasts. And we have the same problems ahead of all our other potential alternative energy areas. The efficiency of the power lines will not let the electricity travel that far. These are significant population areas, so it can help, but it won't be an end-all and be-all. What some scientists have theorized is the amount of energy in hydrogen. Hydrogen comes out of water, H2O, as we said in the very first class here. If you compare a gram of hydrogen, you get 120 joules. Burning gas gives you half that, about 51, less than half that. Petroleum, only 43. Coal, 39. And ethanol, which is alcohol, 27.3. We use green hydrogen from the using electrolysis of water with electricity. Very early concepts, but would be much more powerful, and we have a limitless supply because it is in our water. Biofuel, which we have within our gasoline in the United States, the ethanol, this is actually created from corn stalks and other plant material that's not used for food. It breaks down, decomposes, creates methane, as well as the ethanol. So it distillates. It turns into alcohol, basically. So this is where we get biofuel from. The other byproducts are carbon dioxide. So this is a good way of using residual waste material from food.